So we're finishing with the first set of lectures. So the last section, as you can see, I'm skipping here. Okay, so that's optional. Okay, and then just as a summary of what we have learned in this chapter. Okay, so especially the last part is we started with the model, remember, so that's the key part really. How the model produces, to begin with, the difference equation. Okay, that's the big part of the whole thing. But once you do, then the way we proceeded was to take the limit, produce the differential equation from the difference equation. Okay, so we're going upward, up from the model up to a differential equation, and then the theory of and methods of ODEs emerges. So once again, algebraic solution or closed solution, calculus solution, if you like. Is not very effective frequently. Very easy to produce models that cannot be solved in that manner. Okay, so if that doesn't work, then or when it does, we fall back onto these methods. So theoretical analysis, okay, and so existence and uniqueness of that theory. There is a third one here, so you might. So it's actually there are three of them, but nonetheless, we would just do two. Numerical analysis going backwards, to be clear, as you can see, you see that the arrow has two ends, so it is actually going back to that difference equation. Okay, unless what we received is the ordinary differential equation to begin with, and so that's why we might have not even seen the difference equation, but we might have to produce it as a way to approximate the solution. Okay, so Euler's method produces a sequence of points that approximates the curve. Okay, but not the so to be clear, that's the common misconception is as if this is my curve and this is my Euler solution, and it's not. That would be too good. Too good to hope for. Okay, so it's always off. It's always off, and we'll see how off it is usually. So that's actually the next section. If we were to take care of it, we would know actually the difference. Here there is no difference. The difference is equal to zero between the discrete and continuous is zero. So that's certainly we cannot hope for that. Okay, so it is actually jumps from curve to curve. Okay, that's what Euler solution does. Okay, qualitative analysis. Once again, it is asymptotes, increasing, decreasing, all of that. We did that a little bit. Simplification, which is a big deal. So specifically, we'll linearize our differential equation. The right hand side of the differential equation, it made it linear, and that produces a new differential equation, which we hope has something to tell us about the original one. Okay. Okay, so with that, we're moving on to the next topic, and so we're going into higher dimensions. Okay, so that's what we're starting on. We cannot stay here forever, and so we start with a review of parametric curves. So anybody is not taking or has not taken calculus 3. Okay, so but you must have seen at least some of the parametric curves a little bit. So nonetheless, so it would be a good idea to review it with moving towards high dimensions. It is we cannot stay with one input, one output anyway. So we have to do it. And so we'll just do what absolutely is necessary. Okay, so this is the rotation. We have a rotating rod, or maybe it is not a rod, maybe it is a planet rotating around the sun. Okay, and so we need to describe it. As you can see, invisibly the third dimension pops up. So the everything depends on time. So that's one variable, but then location it will be two numbers. Right? So that's the third. Okay, so as you can see, the description is predictably a circle. Okay, it rotates counterclockwise. The what the location depends on is either time or in this case, you can say it depends on the angle. Doesn't matter. It's entirely the answer is naturally how do we describe rotational motion or rotation or anything like that? What kind of function do we need? What kind of function do we need to describe this kind of phenomenon? Trigonometric, correct. Trig functions, correct. So why so? If we were to look separately at x and y, what did they do? They do this. X does this, y does that, and so that's the periodicity of the phenomenon is what dictates the function that we have to use. And so out of the not so long list of functions that we've got, and we haven't seen them. We have seen actually some in the beginning. You might remember. Trig functions are the ones that appear. Okay, so literally on one hand, on the other hand, is literally the definition of trig functions. You can say that if you doing pre-calculus, maybe you might remember that actually this is the trig function the way they're defined, rather than making a reference to triangles. Okay, so it's literally an angle of a straight line that crosses through the circle, and then from that point we're going down a unit circle. And then on the x-axis we get cosine t, on the y-axis we have sine t. So much so that then that's what requires sine and cosine to go beyond just 90 degrees, and therefore beyond triangles, right? So once the rotation goes beyond 90 degrees, the triangles are out, and so we have to look at actual angle in these two coordinates, the x and y, that depend on t. So there is no triangle anymore to speak of, and and then we speak of projections or coordinates of that point, and on the x-axis we have cosine, on the y-axis we have sine. That's all good. So we will describe this way rather than that way. We look at we split then the responsibility into two. So this is like a merry-go-round, and the two parents look at the kid on the merry-go-round, and they report separately their where he is. Okay, and then they combine the information. So this is the information. So difference. So two functions to begin with. Here they are. So one parent, the other parent. One sees cosine, the other one sees sine, so they do not combine together just yet. And as you can see, so the graph is you can see the graph in green. Okay, well, as I said, oscillation left, right with time, and you can from that picture, especially when that dotted rather than a curve. That's the advantage of a curve. Of a dotted line, a sequence over a curve, you can see how it slows down. You see it, right? Whenever it goes the farthest to the right or to the left, it gradually turns around. Okay, so the dots right here, you can see the dots here. They are denser here. Why denser? Because that is going slower. Okay, in the middle, it passes the middle of the point of view. It goes the fastest. Okay, the picture is very similar or almost identical, but that's the relation between sine and cosine. And no matter how many functions they might produce in trigonometry, it's basically the same function. And so in this case, as you can see, we take the cosine on the left and just shift it pi over to the right, and we have the sine function. Okay, so that little shift is what creates rotation. Okay, so all right, so that's the beginning of parametric curves. Now we jump to the calculus of parametric curves, and that's so far just two functions, differentiate them. So in this case, I'm not doing differentiation literally, I'm doing the difference quotient. Okay, so here's the difference quotient. So based entirely on the data, okay, and how x is changing relative to time, I do difference quotient, the rise of the run, and well, let me see. So for example, what are we seeing here? Slope. What is slope?
Zero.
Close to zero, right? Because right here, right? Okay, so all that information about the slopes is now encoded in the second. Okay, for every single point, as well as on the left and on the right. So that's how it is computed. Right, so the run, change of y or change of x. So this literally, you take these two numbers and these two numbers and you divide and you produce this number over here. Okay, so we did this a few times, but it does not have to be, it doesn't have to be a single function. Now we have two, and they're describing each other separately. Okay, so a lot of information is contained here. Once again, slowing down, speeding up, changing the directions, maximum, minimum, all of that, the relation that you learned in calculus 1 between functions and derivative here, but now you have two of them. Okay, so you certainly can continue on in the same exact fashion. In higher dimension, you have three pairs of columns for x and y and z, and three different quotients and three derivatives if we get to differentiate next. But then that's would be very limiting, and we're not gonna waste our time on that. So the idea is then is to combine together. Okay, just like we combine together two numbers x and y, and to produce to produce a curve, right? So if I take x and y, right? If I take x and y in green and combine them together, that contains this rotation over here. Okay, x and y taken together, that's the parametric curve. So that's if you, as I said, those two the green columns, two columns combined together produces a curve, and then do you keep it this way, or do you do what we already hinted at, or at some point it was hinted, I'm sure. How about this? Does it look familiar, everybody? So rather than having two functions, which it is what it is, but it is productive, more productive to combine them together into one point. So it's point x, y. It's not x and y, each depends on t, but rather you have x, y, a point that depends on t. Okay, so that's the introduction to multidimensional calculus right here. So well, not multidimensional calculus. The next step is multidimensional calculus is what happens to the derivative. The same story, right? So we have here two columns of difference quotient in purple, and just as the green columns are collected together, so do the difference quotients. So literally, so rather than keeping x and y separately and combining function its derivative for each of them, instead we combine x and y to create the curve, and then we combine their difference quotients, x prime, y prime, to produce what? Another parametric curve. Okay, so the what we see on the left is what we already saw it, where everything comes from. X and y, there's rotational motion. We split it at some point, producing a sine and cosine, and now we recombine together, it will produce a circle. Okay, that's the motion. As you can see in a uniform fashion, by the way, you can see how uniformly it progresses. So the angle changes in uniform fashion. You can say another language for it would be to say, what is it? Angular velocity. You can certainly conclude from the picture that angular velocity is so linear velocity is the regular velocity, as we know. So moving forward along the straight line, angular velocity is how things depend on the angle. Or how the angle depends on time. How does the angle depend on time here? Well, to be fair, the circle is not very circular. It's a bit stretched. But the assumption is, well, okay. So what's the angular velocity of the Earth around the sun? It's a trick question a little bit because it's not a circle, but we'll worry about that later. The answer is constant. So the angle changes at a constant rate. That's what rotation is. A uniform rotation, the angle changes, I don't know, 1 degree per second, for example. That's the uniform motion for you. That's not really what we're after. We're still interested in doing x and y separately. Okay, so that's the Cartesian coordinate system that really is way more preferable in the way we just know how to handle it. The question is really, however, is now what is, so we, as I said, I'm not doing anything fancy here. I just take the purple column for difference quotient over for x and the one for y, combine them together into two columns, what is it? It is another parametric curve. Okay, it is another parametric curve because it depends on time, and there are two numbers. It's a point, and that point is plotted. So for example, where is this one? It's right here. Okay, so one point at a time, is every pair is plotted. So okay, so we plotted. The question becomes, what is the meaning of this? What is the meaning of this? The curve on the left we can actually see. If you were to have a drone, say a drone, really that's where's the a drone from above, looking at the merry-go-round from above, you'll see that circle. So that's a circle that's a curve that actually is visible. What about that curve? That needs to be explained. What's the meaning of the new parametric curve that we built? So the derivative of a parametric curve is a parametric curve. Okay, we just need to explain what they're supposed to be, these dots. But before we do, what's the third part for? What is this for? Velocity, acceleration, right? So it will be for acceleration. And I'm not doing it because we're gonna do it later, but you can see that there's no trouble whatsoever. You just for every difference quotient, you compute the difference quotient of the difference quotient, and that gives you the acceleration. That's all. So exactly the same computation that we did from green to purple, we do it one more time, and we have acceleration. So that would be interesting to see what acceleration does to it, and we're gonna examine that unless you don't know, unless you already know the answer. But before we do, the answer is the velocity. What is velocity is supposed to give us? Okay, so those dots are really, they contain information, but we have to extract it. We have to correctly interpret that information. So, for example, well, actually, my error was here probably is incorrect. Zoom in. Look at the labels. Okay, so the labels. The labels are the labels of time. Okay, so the label of time. So the first one, it corresponds to time equal to 0, and I do believe that this is where we are. One or the other one. Okay, so well, let's pick one. Let's say this one. It's pretty close. Okay, so what is the meaning of this dot in terms of velocity? What is the velocity anyway? So it's two numbers, obviously, because the first number comes from the rate of change of horizontally, the other one in the vertical for x and y. If we combine them together, we apply the point. What's the meaning of that point? It's not as much of a question as the answer, actually, but the question is, what's the meaning of the velocity in the two-dimensional sense? So if you're describing motion on the plane, what is, and you say velocity, what do you mean? Well, it could be linear, but what is the definition of velocity? Say one-dimensional case. What's the meaning of the velocity? What's the meaning, the definition of the velocity, and what is it good for? Velocity.
Position over change in time.
What?
Like change in position over change in time. Is that what you're asking?
Right. Yeah, but can you be more less mathematical, more physics related, or what's the practicality of the issue of the concept?
Speed.
Okay, speed is warmer, right? So in other words, how fast we're moving. So and that was a single number. It's one dimensional. The velocity was a single number, and if you're considering speed, okay. So but if you speed, remember what speed is. It's how fast, ignoring what direction, right? So it is how fast and in what direction. Okay, so then that's one point over there supposed to contain both of them. Okay, it contains both how fast, the speed, and the direction. And what direction in the two-dimensional case is determined by, and the answer is a vector. So that's, we plotted as a point, but that was a mistake. It is a parametric curve, but it's not made of points. So these are not points, but vectors. Okay, so then that point, for example, that point that I plotted there is actually will look like this. Okay, do you find this helpful? So the time is t0. We are at 1, 0 over here. And we also have computed the velocity, which looks like this. So what are you seeing? But that arrow pointing up, what does that mean? It's the direction. It's if you are here, the rotation is this way, and if you're here, which way you're going, this is the way you go. For a moment, remember, we speak of the instantaneous velocity usually, and in that case, it will be pointing in the tangential direction. Right, so that it is a match between what we have computed over there and the picture that we have on the left. So as long as the 2 points are matched, the where we are and which way we're going, then the interpretation of that point as simply the endpoint of our vector then points out in the correct direction. On the other hand, if I were to look at, say, this point, right, this point right here, okay, so the arrow points this way. Makes sense again. Okay, so that's what's behind this little computation. We are pointing, and the arrow is where we're moving for at that moment of time, pointing both the direction, how fast we're moving, and how fast we're moving. You can guess if this is a circle, then how fast? What's the speed? What's the speed? Judging by the picture on the right. The direction is changing all the time, right? You can imagine if you're driving, if you're sitting on merry-go-round, and you see that always direction keeps changing, as if you're sitting on merry-go-round and you feel like you're doing this, right? Like this, the rotation. Okay, but what about the speed?
Speed's the same.
The speed is constant, that's right. Because if this is a circle, and it does look like a circle, then yeah, then the distance from the center to the length of that vector of that arrow will be constant. Which, yeah, that's indicates that the speed is constant. Okay. So anyway, so this is a computation of difference quotients. Okay, the second one I skipped. We speak of the vectors, deserving more attention later on, which is introducing this idea. And then this is how I can produce a bunch of circles. So I picked a point in the middle right there. So I actually started from the right, and I took that point, but did not think of it as a dot anymore, but rather the end point of my arrow. I took that arrow and copied it over there. And then what do you know? It actually fits exactly right. It points in the tangential direction. And so all of these curves, I don't have it here, unfortunately, but every single one of them will be roughly like this. Okay, so that's if you are to plot all of these arrows like this, and then copy them to the picture, to the corresponding point, then they'll be looking like this, like two tangents. That's the same length of an arrow that is being rotated. Okay, so that's the description of the velocity, and we're going along the circle. Before want to guess what the acceleration is? You probably know the answer, and so, but if not, maybe not for the merry-go-round, but imagine that this is actually a planet going around the sun. Which way is the acceleration? Towards the sun, right? Towards the sun, that's right. So this is, yeah, so it will be roughly, so so it will be like this. And why so? Because acceleration, that's according to Newton's law, acceleration velocity, acceleration force is the same thing, and the only force is the one that the gravity force, there's nothing else. So we have then all the information here. We just did not compute the second derivative because we haven't done any second derivatives, right? So we spent a whole month and we didn't do any second derivatives, and so no second derivatives, no forces, no Newtonian physics really, but rather we're just dealing with the first derivative for the time being. But it's all there. So if the function is there, then the first derivative is there, the second derivative is there too. Okay, all right. So let's specify some things about what we are facing, and that's what it means to have a function. It is nothing but a black box that carries out computation from the input into the output. Neither input nor output has to be a number. So that's calculus 1 that's been going on for too long. And now neither input nor output has to be a number. More likely, it is going to be either a point or a vector. Regardless, we already have an example of how the output is now is a point right here. Okay, so a point like that, and it depends on time. So you can do differentiation if you want. Okay, so that's pre-planned, and so as long as you can carry out the algebra, you can carry out also all the calculus operations as well. So but then the general setup is this. So any input is possible of any dimension and any output also of any dimension. So what varies is that these two numbers n and m, the number of dimensions, number of variables among the inputs, and the number of dimensions among the outputs. That's a general classification of functions that is sufficient to cover all calculus, including the multidimensional calculus. Okay, so this is the table that I want to put forward. Domain versus codomain. So once again, they remember this notation that this is notation. Okay, so Rn to Rm. So I hope you've seen this notation indicating the Rn is the Euclidean space of dimension n, the Euclidean space of dimension m is the output, and then varying the two numbers produces a variety of functions that all you can imagine, covering the whole calculus. So calculus 1 is right there in the box. Dimension 1 in 1. Input is one dimensional, output is one dimensional, right here, bottom left. Okay, and so you're doing these graphs, and everything is the curve on the xy plane, and it progresses from left to right. It cannot come back. Remember, you cannot turn back. And therefore, the curve right there, up there, is not part of calculus 1 because that graph cannot represent a function, right? That at the top. So then what happens is, and that's the primary example of parametric curve is top left. That's a parametric curve. So the input time is not present because we're plotting it on the plane on a piece of paper, and there are only two dimensions there. So do you see the third dimension somewhere? Where's the third dimension? Input 1, output 2. The two dimensions is the plane. Where's the third, the dimension that refers the input direct dimension? Do you see it? Look carefully. Let me zoom in for you. You see it now? You see? The time, that's right. These labels, it actually is done with Excel. So Excel automatically will plot it for you. If you have 3 columns, you plot the 2 columns as we have done. And then the third column can be, there is no room for the third dimension, but you can use it as a label every point that you plot. And that's what happened. So then you can see how you're progressing, and the one that Excel can also do, it can also give you the arrow indicating the direction. So that's what makes the difference between a curve and a parametric curve and something else. And just the graph is direction, and but the numbers are sufficient because you go from t equal to 0, t equal 0.2, 0.4, and so on. And that's my parametric curve, and it is visualized, which is the way it's just custom to visualize parametric curves on the plane, and hiding the the parameter dimension, the input dimension, the time dimension, somehow, in this case, we're hiding it, we're not hiding it, but we're presenting it in the form of labels. So when you are, so where you are, you can see it on the XY plane. When you are, it's a label. So it's a, imagine taking a hike through, or planning a hike or through a forest, then you have a path, but also for any for that to be of any value, you also every location where you are, you labeled with a time where when you were there. So that's how we visualize parametric curves. Okay, so that's where we're heading for. It seems that this is calculus 1, but also now we're let's go to the second column. Two variables, single number output. Okay, so once again, it is calculus 3. We're not going to study them, but we've seen them already. I remember when we saw this, bottom right, when we saw this. Function of two variables. We've seen it a few times. Remember this? What is it? What's the context? FTY. It is a function of two variables, as you can see, but what's the context?
You put in two variables and you get an output of another variable or another number.
No, it's just the right-hand side of the differential equation. This is the context. Okay, so yeah, remember that's your direction of your motion, how your derivative is determined by where you are, y, and when this is t. Okay, so even though we concentrate primarily on if there's no t, it's called autonomous. So we primarily concentrated on autonomous equations, but that nonetheless, this is still a very important. We've spent plenty of time doing it. So a function of variables is present implicitly, but it's a setup. It's a setup. It's not. The answer. So this is what we're heading for. This is the solution. This is what solutions will look like. Okay, so if that's exactly what's going to happen. Yeah, like this. This is what up until now. Until now, the right-hand side. So on the right, I have my ODE here, and on the left, I have a solution of that ODE. Right. So ODE is actually determined by a function of two variables. Its answer is a function of one variable. Its solution is a function of one variable, right? So that's all there is. So what's going to happen now is so we're going to have y prime is equal to not y prime. We're going to have well, anyway, we'll speak of ODEs later, but right now the solution that we're looking for high dimensional equations. Well, I think this is appropriate. So this is my ODE. Once again, I'm not trying to write it yet, but that's what it looks like. It's a flow. So you once again in calculus 3, you might have seen these, but we're not going to study them because we only look at them as the setups. So these more complex functions on the right are actually the setups. They just provide you the model. They have come to from model. So these are the models. Model for some kind of flow of a liquid on a plane over here, and this one may be something else, but it's still nothing but the model. Okay. So and then, but what theory of differential equation does is how to, if you are given this, you know where every direction is. How do you fly through that? If maybe it's a liquid, maybe it's an air, and then you have to indicate which way you, in a natural way, that wind or that flow or will take you, that current. Okay, so and that produces a solution that might look like this. A parametric curve on the plane. So the directions are supplied on the plane, that's at the top, and then the solution or solutions more likely will look like this, like on the top left. Okay, so that's just once again an introduction. So but the parametric curves, we can think of its input being output a point. but we can also think of it as a vector. Output is a vector. Function of the variables, the same story. The input might be a point or might be a vector. It's just two numbers and depends on how we prefer to look at it. Sometimes it's a point, sometimes it's a vector. If we want to do algebra, then vectors are preferable because it makes more sense to do algebra with vectors. For example, you have two forces, you know what you do to the force at the end of the together. Same with velocities. Okay, so vector fields, that's the top right, which is what we're going to start dealing with, tell parametric curves which way to go. So remember in the past we had a slope field, which would tell us quite a while ago by now, which will tell us where the curve is supposed to go. So this is very similar, except the time variable is hidden. Okay, so either we concentrate on distances and locations, the geometry, or we concentrate on directions, in which case we're going to be doing algebra. Okay, so parametric curve we refer as a parametric curve here. Any function of the real variable with the domain inside the reals might be time again, and the outputs in possibly m-dimensional Euclidean space. Okay, so naturally we've done this. This one is done, and then this one is next. Two-dimensional. But once we get the idea how to do two-dimensional stuff, the three-dimensional is not variable. Okay, so let's look at some parametric curves. Once again, ignoring ODs for now, and just look at some simple parametric curves. The simplest one is a straight line. It's determined exactly by a single vector. Imagine that everything is just flow. Think about Newton if you want to think about Newton again. So in this case, no forces. A forceless universe, if you can imagine that, then everything moves along straight lines without acceleration. That's what it is. So you have point, but let's utilize vectors here. Let's a very simple situation that we have here. Let's rephrase it in the language of vectors as much as we can. Okay, so the point is, so 0.13 is the starting point of our motion. Okay, and then the constant velocity is 2, 3. So it is plotted right there, which means that say you progress in that direction 2 horizontally, 3 vertically every maybe second. Okay, so that's the setup, and then so that's the setup. Okay, naturally the x and y axis could be moved elsewhere, and it would still make perfect sense. But since we are supplied with the system, then we can also express that we actually move 2 feet per second horizontally and 3 feet per second vertically. That's what 2, 3 means. Okay, so then like this. Okay, and then let's do some algebra. Naturally, once we determine what was happening in the horizontal vertical directions, then we can describe motion in its entirety if we like. So, but let's look at the vectors nonetheless. So if P naught is our original location 1, 3, and notice that, by the way, the point to the notation is 1, 3 point, 2, 3 with triangular brackets is a vector. It's not really required to do it, but I just prefer to distinguish the two, so there will be no confusion. So okay, so if I'm at 1, 3, yeah, I progress by 2, 3, I end up with literally adding them component wise. 1 plus 2 is 3, and 3 plus 3 is 6. Okay, right? 3 and 3 gives me 6 over here, and over here I have 1 and 2 gives me 3. Okay, so I progress to the next location right here. So the next location is 3, 6 after 1 second, and that's P1, the next point. So there it is. 3, 6 is the next location, and you can keep going doing that as much as you like. But also, it's not really a sequence because they're in the middle. We can imagine that we're continuously progressing from the first point to the second. Okay, so then that's how we write P of t, function of points, and it is determined by two numerical functions, x of t and y of t. Okay, and we just combine them together. So if we now, and we go back and forth, so we combine and then we recombine, assemble, disassemble. So I assembled them together just now, and now I disassemble if I want to look at x separately from y. And so x of 0 is 1, and then x of 1 is 3, and then in the meantime, y of 0 is 3, y of 1 is equal to 6. So I'm progressing in these directions. These two are independent. Okay, so that's the thing about it. Once you do, then actually the problem is solved very effectively. Look at it. One, we know if the motion is linear, and we know 2 points determine a line, so we easily can figure out that actually the y-intercept is 1 and the slope is 2. And slope is 2, right? From 1 to 3, the slope is 2. And y horizontally goes by 1. And the slope is 3, and the x y-intercept, well, x and y-intercepts, so that doesn't apply, but so I'll just I'll let you check this. That indeed, if a linear function is 1 at 0, 1 and 3 at 1, then it is 1 plus 2t. Okay, and then similarly, 3 plus 3t gives me the second term. Okay, so these are two separate ones. Once again, as if two parents looking at the behavior of the kid, linear motion. This is a parametric curve. But this is a better way to do it. So now I'm reassembling it, these two together. And so, so x of t, y of t is 1 plus 2t, 3 plus 2t. It is a point that depends on t, a point. Okay. So what is the point? There's a point to it. Why assembling is productive, especially at the high dimension. The higher the dimension, the more effective it is. So let's carry out this little bit of algebra. So 1 plus 2t of 3 plus 3t, it is a complete description of motion. So we don't really need to do anything. Okay, so hypothetically, but actually it is revealing to actually just combine the terms together. Okay, so this is what I do. I split it into two terms. 1, 3, 1, 3. The point that just happens to be the initial point, and then I have 2t, 3t. You see what happened here? So I'm decomposing my function into, rather than decomposing the separate for coordinate x and coordinate y, I'm looking instead at something more meaningful. And so as you can see, what I have extracted is 1, 3, which is the initial position. Okay. What remains to be seen is what is the second term. What's the second term?
Rise over.
What?
Rise over run.
Thank you.
Like rise over run. So that's not velocity.
It is, well, no, you see rise over the run, it only makes sense if you speak of,
Two, like 1 to 2.
the two slopes. Or 2 is the slope and 3 is the slope. Or if you were to actually look at x and y separately, x against t here, y against t there, then you can speak of the slope and you can speak of horizontal, vertical velocity separately. But that's not actually the preferred idea. Is actually to do this: factor t out and look at t3. Okay, so then not only we going algebra backwards, we actually extracted not only the initial location 1, 3, but also the velocity, the constant velocity to 3 is also has been extracted. It's there. So the vector algebra, which is what we use here, actually produces a meaningful representation of our motion parametric curve. So P naught, the initial velocity, the initial position, and then in the velocity multiplied by t. So velocity is as a vector multiplied by t, which makes you progress forward farther and farther. For each t, you will find a location like this. How? The location, which is the initial, and then the initial vector multiplied by a lengthened or shrunk, depending on t. And so to give you your every single possible other location on the curve. So each t will produce a new location. Okay, so naturally, what is this? As I said, so vector algebra comes into play here. This is a stretch of v. If t is larger than 1, it's a stretch. If it's less than 1, it is shrink. But nonetheless, you stretch it, and then you take that vector, which gives you, if you multiply velocity by time, what do you get? You get that displacement, right? So displacement, also a vector, is then copied and attached to the point where we started. So location plus displacement gives you the next location. Okay, so that's the presentation. The simplest motion, once again, there are no forces, and that's the great thing about it is that look, appreciate the formula. Okay, so it surely looks simple. Okay, so if you know what's behind it, then you can appreciate the power of it and how we move from one-dimensional motion to two-dimensional motion. I'm using a capitalized letter here to emphasize the difference between vectors and numbers. So t is a number, lowercase. P is a point, two-dimensional. P naught is a point, two-dimensional. Vector V is also a vector, two-dimensional. So then, and that is the algebra of vectors here is being carried out for every t. Okay, so because the velocity is constant, there is nothing fancy happening. We just progress one v at a time, and then every proportion of v is also there, and so we end up with a straight line, which is happens to be parallel to v. Okay, so the v itself is 2, 3, so you can actually plot it separately here. Technically, every vector starts at the origin, so that's my v really. And then if this is my initial p naught, this is v. So what happens is I copy v and attach it to the initial point, or I first multiply v by something. So I can say maybe this will be 2v, right? So if I take that 2v and copy it to start with p naught, and that will give me the progress as we're moving after 2 seconds. Okay, so that's the way what we're gonna adopt here for the rest of the course. Parametric curves written in vector notation as much as possible, including all the calculus. So we're gonna differentiate this too. But once again, at least it doesn't have to be more complicated than it has to be. So we start the same way as we started with the one-dimensional case. It's really about models. Okay, so how to set up a model, which is just the difference is there will be more variables to worry about, so it will be more complex. But the mathematics hopefully will actually look as compact. I don't want to call it simple, but it certainly is compact because it compares to compare this and that. And then even though it's the same thing, it is more compact. And so not only that, you can go to dimension 3 or 33, doesn't matter, it will look exactly the same. So your motion is through 10,000 dimensional space of whatever maybe stock price is saying. Okay, so and then it will look, as long as it's constant speed, it will look exactly the same. So p naught plus t times v, and then that's really the power of vector algebra. Okay, so linear motion. Position at time t is initial position plus t times velocity. So once again, relying on algebra, and this is if we were to have a string of generalizations. Dimension 1, a plus tb, that's calculus 1. Then now we're looking at which we just did. A, b, the initial point, plus uv is the vector of velocity multiplied by t gives you the next location as well as the rest of the location. What's the difference if we go to dimension 3? Not much. You just have ABC, which is just everything has an extra third coordinate, and then so you know that the fourth one will have 4 and 4, and so what was really the point? Instead of this is much more compact and easy to think about location, written in terms of initial location and the velocity. Once again, we're carefully capitalizing that are multidimensional entities, and we're to keep if it is a number, it's a lowercase. Okay, so in fact, so the initial formula has been capitalized, and it's almost the same thing. So b that used to be a number, now it's a vector. The initial location a that used to be a point, now it's a point on the line. Now it's a point in space. And once again, everything that we do will be equally applicable to any dimension. Harder to imagine or visualize, but nonetheless, if we go carefully through these steps, then this will not really constitute a big of a problem anymore because every visualization that you have in your mind will be probably 2 or 3 dimensional. Okay, so parametric curves of uniform motion. Once again, this you can think of this as a definition. This formula already is available. This is just for the record. The initial position is given, and the velocity is also initial velocity, which is the same as actual velocity because it's constant. with velocity, so it's really not initial velocity. So any questions so far? So the motion naturally has that extra dimension for time, but the spatial dimension is m. T, okay. Constant velocity, once again, that's the picture. You can carry out, so here, there's this example that was done for a linear function, and here it is done for what if we were to do the same thing, but with as a sequence, okay? And then the recursive formula is very simple. As long as you picked delta t appropriately, then you just multiply and progress every time by the same number. So x progressing by the same number, y progressing by the same number, which means that the vector every time is repeated, and you produce a bunch of points moving in the same direction. That's what you get on the way. So that's all there is. Now let's go back to something that you must have seen maybe in high school math or physics. It is the motion of a ball, but now we would spend some time in this course throwing the ball, but we throw it up. So what if we throw it forward now? That's an extra dimension. Okay, so basically we have all the tools available to us. We know how to describe it. That is the Poynting curve, okay? And we also know that takes some insight, but I'm not sure when they came up with that idea, but the motion can be split into horizontal and vertical, and they are entirely independent to begin with. And then that is the insight of, I don't know, before Newton, there was idea came up that there is no horizontal force, and therefore there is no acceleration in the horizontal direction, and therefore the motion will be linear, okay? In the meantime, there is a force in the vertical direction, therefore there will be acceleration, okay, or deceleration down. Okay, so that's roughly what you have. Once again, x dimension is plotted on the left, the far left. Okay, so it is linear because there is no force, there is no acceleration. So forceless motion is a linear motion. And for y in the middle, you have a vertical motion, the vertical down acceleration. That's why it goes up and then it has to go down. Okay, so once again, I have it here. Right here is the 3 columns of numbers. The first for t time, and then x horizontal, y vertical, and then to visualize, we pick the right two. X against t, then y against t, and then the third one is really most interesting, is x against y, y against x. Okay, so it's still a parabola, but just different, slightly different shape. So t once again is used as it's called the trajectory of the Poynting curve. T is still present in the form of those labels, and you can see how if you're not entirely comfortable with the Poynting curve yet, you can see how it has happened. So t equals 0, x equals 1, t equals 0, y is equal to 4. So I take these 2 points and then I produce 1 point over here. X equal 1, y equal 4, t equals 0. That's a point that we combine together. So at t equals 0, x 1, y 4, which means that plot 1, 4 right there. This point is what I plot. Okay, we just do it one at a time as many times as necessary. So if it is just a sequence of numbers, then or 3 sequences of numbers, I just do it with the help of a computer. So Excel does it very easily for you. So the red curve, the trajectory is actually what you see. So if you see a streak in the night sky, that's what you see. You don't see these 2 graphs. These are abstractions, horizontal and vertical motion that looked at separately. Okay, so this setup, and that's the key to it, is this no acceleration in the horizontal direction. Okay, and then let me make it clear. There is a wall between x and y for now. Why so? Because all the methods that have developed have been one-dimensional. So let's just apply these separately. Fortunately, there is no interaction between x and y, so we can solve them in entirely independent fashion. So if we know the acceleration, we can find the velocity from it, and from the velocity we can find the location. Okay, so this is to make it specific, and that's if we're doing this numerically, we need the specificity of the actual number. So here the elevation is 200 feet elevation, and the horizontal velocity is 200 feet per second. Okay, so we want to find the trajectories for this. for the purpose of, shooting the cannon and landing it. So initial location P naught, at P naught, and Y, and, hold on a second, that's, the right, it's a Q, right here. It's a Q, and this one is a U. Yeah, so it's happening. So because we can get away with just the same letters for X and Y because they're different, so there will be 4 X's. You have the initial location, initial location for X, which is 0, and for Y, which is 200, and for initial velocity is 200 for X and Y for Y to 0. There is no vertical component, as you can see, we're just shooting it forward. And then, as you can see, once again, we know recursive equations, how to find the location from the, I'm sorry, in this case, to how to find the velocity from the acceleration. Okay, so we only using this part, and that's what's happening here. So it's very simple. So you just multiply the acceleration by delta t, and that gives you the increment of the velocity, right? So that's what the meaning of the acceleration. So acceleration changes the velocity in what manner? In this manner. So you just multiply by time, it gives you the increment, and so that's what it is. The only question that I might prefer here to address now is, let's do it even though they are separated computationally into 2 separate computations. Nonetheless, it still makes sense to combine them into vectors, and that's what I do here. So point x, y, which is a sequence v, which is also sequence, okay, for x and y directions. And then the acceleration is very simple because they will remain forever. Horizontal component of acceleration is 0, and vertical is -g. Once you have it, you can find the velocity, which is what I do. Okay, so the computation, so later on, the next one, I know it's, it's already here. So the velocity is found from acceleration line number 1. We did this before, right? But this time it is a vector formula. And then the second one, we're finding the position from the velocity, so two-step procedure. And once again, the formula is a formula of, based on vector algebra. Okay, so the vector, each vector that you just found multiplied by delta t will give you the displacement, and that's how you find your next location, and that's how you progress on. Okay, so that's the, once again, writing, if we were go to derivatives now, x prime, y prime, let's just write x uppercase for the point, and then we just write x prime, and we write x double prime, because it's the parametric curves can be differentiated in a component-wise fashion, just the way you see here. Xy is my position, then how to find the derivative, to differentiate the two. For the acceleration, differentiate one more time. So it's everything is very similar to what we had. If it's computational, it's recursive. Instead of having two columns for t and x, say, we have 3 columns for t, x, and y. Okay, so story the same. If we were to talk about calculus, then there is an extra derivative to be computed, but that's all. Okay, so, I see, I remember now. So this is, anybody seen this meme before? Anybody seen this meme before? Label these things. What?
Like gas and brake.
Okay, so this is gas, right? Oops. What are you doing here? Gives me some. This is gas. I just want to write gas. Okay, gas. And this one is brake. Right? Brakes. And then there's the steering wheel. Okay. Well, okay, so there's another name for gas. Accelerator, yeah. Okay. So it sounds more scientific, frankly. How do we rename brakes in a more scientific manner?
Decelerator.
Yes, it would be, but even more scientific would be what? It's still accelerating, just acceleration would be negative. right? So just as well, brake is also an acceleration, just we apply with gas, we give positive acceleration, and therefore with the brakes, we give a negative acceleration, so it's still an accelerator. Okay, how do we call the steering wheel,
Something.
which is what? It also accelerated, that's right. It's also an accelerator, so can you explain why we call steering wheel an accelerator?
It's just you're going in a circle, you're changing your.
That's right. Yeah, you're changing the direction, but how do you change direction without changing the velocity? So if we're going straight, and so maybe your horizontal direction was 0, and maybe this is 60 miles an hour. So, and then when you have finished the turn, it's the opposite, 60 miles an hour this way and 0 that way. So that's your accelerator. Accelerating in one direction, decelerating in the other. So that's a kind of either calculus or physics or in the spirit of mathematics. You can just rename everything. If we speak of acceleration, then why not just know what is that? It's engineering. In terms of engineering, you have 3 different devices, but they're doing the same thing. We're controlling. There's only one thing to be controlled as far as the cars is concerned. It is how fast we're going, and so we change that direction. And we now know that how fast and the direction is pretty much the same thing. So velocity captures both the speed, how fast, what the speedometer shows, but also the direction. Okay, so and then we change them with these 3 tools, varying them very, very carefully. And but we're doing the same thing. So from scientific point of view, there is nothing else but one operator, and you probably can have one if you really try. You can probably combine them together in one single apparatus. Okay, so once again, recursive formulas. That's what I just explained to you, right? So if the x double prime, y double prime are unknown, and as you can see here, they are. X is that's the column. X double prime is 0, no force, and forever. No force in the horizontal direction. In the vertical direction, negative 32 pound per second squared. Okay, negative 32, and then we are carrying out the computation from x double prime to x prime, and then from x prime to x. So from acceleration to velocity, from velocity to acceleration, using that summation formula that we used several times. And then, as you can see, because there is no acceleration, the velocity then remains the same in the horizontal direction, and therefore the progress in the horizontal direction will be uniform every time I move forward by 0.3. You see, right? So that's the very simple motion in the horizontal direction. So constant acceleration, 0 acceleration, constant velocity, and then linear progress in that direction. Okay, so every time I progress by 0.3. In the meantime, here it's certainly more complicated in the vertical direction. But so you cannot do it without actual computation, but it's done for you by the spreadsheet. So as you can see, it computes the values, and negative 32, so it goes 0, and then 0.1, negative 1.9, negative 2938. So as you can see, it is what is it? It's the horizontal you go faster and faster in the negative direction, right? So 0, negative 0.1, negative 1.9, so it goes faster and faster in the vertical direction. Okay, so that this is the formula for the computation. The problem also interesting to address is, and that's frequently is the problem is, what is the best angle? Remember that problem? What is the angle of your cannon should be to shoot it at the longest distance? What? 45 degrees, but only if you are shooting from the ground. If you're shooting from elevation, it's not the case anymore. So, and you can using this kind of spreadsheet, you can test that idea very easily, and you'll notice that the higher you are, the flatter you have to shoot in order to shoot the. Okay, so that's the computation recursive formula. Okay, so all right, so that's an extra thing. If you're what's it called? What is called the velocity of the cannon. It's always the same. You don't really vary the muzzle velocity of the cannon or gun, and so then you control the distance by the angle. Okay, so that's what this problem is all about. Okay, so and then if you were to aim, and you're to aim, then you have to pick the right angle. Once again, you cannot vary the amount of gunpowder in the cannon in order to hit the target. You have to change the angle. So it's a big deal, and so it's certainly at some point it was really a big deal, but it actually took a few centuries after Newton came up with all this business to actually make it practical and use calculus in artillery was only realized by the end of 19th century. So they basically did not just did trial and error. Okay, so if we were go into the continuous case, it's really very simple. So let's run this quickly. So that's all. The whole problem is right here. X double prime is 0, y prime is negative g. Okay, and then we integrate. Right, so then from x double prime, we find x prime. What's x prime? What?
What's the question?
If x double prime is 0, then what is x prime? Constant, right? So then depending on your initial velocity, dx, it will remain the same, so it's constant. And then with the second one, negative g, when you integrate, you end up with a linear function for the velocity. Okay, so once again, the initial velocity is present as v sub y. Okay, and then you must have done this before, but probably with one direction at a time. But then now we integrate one more time. Okay, so then my constant becomes linear and my linear becomes quadratic. Okay, so that's where -1 half gt squared comes from. We integrate negative gt, and then the constant that we remember, that plus c that we keep repeating. That's the meaning here. It will be in the first integration it was the initial velocity, and the second integration is the initial velocity. Okay, so that's then this description. Let's that's what we have here. The depth is initial depth plus initial velocity times time. So that's very simple progress. And then for the height, initial height plus initial vertical velocity times time. And this is the last one is the acceleration. So the time, it depends quadratically on time. So that's the how you can classify it easily. Linear depends on time for the horizontal, and quadratic depends on time for the vertical. You can combine them into vectors. Once again, that's vector solutions. And it's a uniformly accelerated motion. Okay, so that's what we have here. That's the equation. As you can, but I have written it in the form of a vector equation. Okay, so P naught, B naught, and A are actual vectors. Okay, so acceleration is a vector, velocity is a vector, position could be vector too in this case. So the problem has been solved. Actually, the one I ran into this morning into as nice as these formulas are, these formulas especially. So this is, yeah. So this is actually once again, I'm not sure. Let's call it attributed to Galileo, even though it was done before him, but that what he's famous for, among other things. And running out the equation in terms of explicitly motion as horizontal, motion is linear, and a vertical is horizontal. So this morning I ran into a quote from actually Einstein about Newton. And then what he especially credits him with is that laws of nature are differential equations. So this is not a differential equation. Up until Newton, the laws of nature were written explicitly like this. Okay, the formula, and they just plug it in, and you have your you know what's happening. Okay, so that's what the motion of a free prone object would be governed by the equation. So they actually studied in high school. Okay, but what Newton did, he would express the things in terms of differential equations as that's how the laws of nature are supposed to be written, as differential equations. So this would be Galileo, and where's Newton? This is Newton. Okay, and so once you take that route, then you can vary. It's much more productive because now you can consider things that are maybe entirely different by nature. So maybe there is a horizontal force applied in addition to nothing. So if with gravity, you can add a force, for example, maybe horizontally there's a spring, right? There's a spring, and so then the motion will be very different. But you describe that dynamics by means of once again differential equations, and one for each of the dimensions. Okay, so I'll stop here. So see you next time. Dismiss.